So let's look at this example that we've already studied in part one, but this time we'll actually work out the exact critical value and the critical regions. So you're familiar with this example, and we'll set up the alternative and the null hypothesis. So we'll define P as being the probability of guessing correctly, and therefore our null hypothesis is a quarter, and the alternative hypothesis is greater than a quarter. Significance level is 5%. So let's define X to be the number of correct guesses, and therefore if H0 is true and P is a quarter, we can establish a binomial distribution where n equals 10 and P equals a quarter. Now in part one we solved this by using the probability regions. This time we're actually going to work out the exact values of those critical regions. So what we're going to look for is the lowest possible value of A, and the reason why it's not the highest or lowest is because of the inequality over here. We want where X is greater than A is less than 0.05, and so we're looking at the right side of the distribution. And so if we rearrange this, we've got one takeaway, the probability of X less than A minus 1, because they're discrete values, and that's less than 0.05. Rearrange that and we end up with something with 0.95. And if we, from our tables, we can see, and it's good to put down both values. You've got X is less than X is less than 4 or less than 5. Clearly, when X is less than 5, that's when it's greater than 0.9803. And so the lowest possible value of A, therefore A minus 1 is 5, and so A has to be equal to 6. So we can therefore conclude our critical value, which is like the boundary for the critical region, is when X equals 6, and the critical region is when X is greater than or equal to 6. So this person got 5 correct questions, which doesn't lie in the critical region, and so therefore we accept H0, and we can conclude that there is not sufficient evidence to suggest that students actually do better by guessing. So this is what it looks like on the graph. We found when X is less than or equal to 4, which is here, we get 0.9219. And when it's less than or equal to 5, we get 0.9803, which is what we want, because we want something which is greater than 0.95. So with the 0.9803, if we set that value of X equals to 5, which is A minus 1, then A equals 6. We can clearly see when A equals 6 over here, then that's where the critical region starts. So critical value, I'll just write that down, is when X equals to 6, and the critical region is when X is greater than or equal to 6. And so this person who got 5 correct, their answer doesn't lie in the critical region, and since it doesn't lie there, we accept H0. Right, let's visit this example again, and it's a case where 6 people pass. There's a probability of 0.8 of passing. 6 out of 10 students pass. Should the head of maths be concerned? So, in this example, which we've met before, we'll define P to be the probability students pass S1. Obviously set up a null alternative hypothesis and define X to be the number of students passing, and we have a binomial distribution, n equals 10 and P is 0.8. Now we can see from here that when P is less than 0.8, we're looking at the left tail or the beginning of the distribution. And so rather than solve this like we did in part 1, where we looked at the probabilities, what we're going to do is work out the actual critical value and the critical region, and then base our answer on that. So the highest possible value of A is now what we're looking at. And we want the highest possible value of A to be less than 0.05. If we rearrange this, or if we look at our tables, in fact, we'll find that we have two options. Well, there's two values that in the region we need to look at. One is obviously at x is less than or equal to 5, we get 0.03, and if you go one above, we get 0.12. So we know that that's our the region we need to focus on. Now we get obviously less than 0.05 when x is less than or equal to 5, and so therefore A equals 5, and our critical value is x equals 5, and the critical region is when x is less than or equal to 5. So if 6 students pass when x equals 6, this doesn't lie in the critical region, so we can therefore accept H0 and conclude there isn't any sufficient evidence to suggest students are underperforming. Okay, so here's a diagram of what we've just calculated. We can see when x equals to 5 for a distribution where n equals 10 and p 0.8. That's where our critical region actually starts. So you've got critical value of 5, critical region when x is less than 5, and this person got 6 students passed, and therefore that value x equals 6 doesn't lie in the critical region, and we can accept H0.